So, in the previous class we have learnt about the average speed, the RMS speed and the most probable speed. That means, in a gaseous system or any system, the molecules are in random thermal motion, and in physics we describe the motion of a molecule as a random walk problem or the motion of a drunkard. So, if we follow the path of an individual molecule, we will find something like this. So, let us follow, this is the single molecule and we have labeled that molecule. So, it moves with certain velocity and then it gets a collision from other nearby molecule, it goes here, then again it goes, then again here it collides, again he goes, again here one more collision, then again here collision, then again this collision, then this collision and then this collision. So, this is just a random walk problem type. So, just you think that a drunkard moves here and there, and in this way the molecule goes on. So, this is the path a particular molecule will follow. So, you see, so the path is generally straight unless it collides with the other molecule present. So, this is how the molecule's actual path will be random, it will be random. So, if we follow the path of a particular molecule, then the path will be like the figure shown. The straight paths. So, during the straight paths, the molecules move undeviated, but at the sharp ends, it encounters violent collision with the nearby molecule. That is why its course changes. So, these dots where there is a violent change in its velocity is due to the collision. So, the distance that is, we will see the average distance. The average distance a molecule covers before encountering a collision is called mean free path. So, let us calculate the mean free path of a molecule. So, this is the meaning of the mean free path. This is the average distance a molecule travels before it collides with another molecule. So, now let us calculate the expression for the mean free path of molecules in a gaseous system. So, we denote this mean free path by L bar. So, now you see here, consider a molecule of radius r. This is my molecule A, which is moving in this direction. So, this is the axis along which the molecule is going to move. So, consider a molecule to be a hard sphere of radius r. So, we will assume its radius to be r. This molecule is moving, let the average velocity of the molecules of the gaseous system be V bar, or we can also write V average. So, presently I can use this or this, any term I will be using. So, this is the average velocity. So, my molecule will move with this average velocity. So, now you see it moves, so it sweeps out a volume contained in the cylinder with the cross section area of this, that is we will say pi r square. This is the molecule with the cross sectional area pi r square. So, this molecule will sweep out this cylindrical volume. Now, it is going to collide with any molecule like this. If a molecule is like this, it will collide with this. If a molecule is just touching it, it is here, that means suppose I say this is A, this molecule is A, this colliding is B1, B2. So, A, and suppose let us assume that these molecules are stationary here, suppose they are stationary here and this is only moving, then it is going to collide with B1 but not with B2. It will collide because B1 comes in its boundary, but it will not collide it with B2. Similarly, I can consider a molecule here, that is molecule B3. So, this A will just avoid a collision with another molecule B3. That means, if anything comes within, you see suppose they have all identical radius, that means B3 should not, any molecule B should not come within this one. If it is here, you see if it is suppose a molecule is here, then it is going to collide here. If a molecule is here, then it will not collide. That means the molecule, this molecule whose radius just touches this dotted boundary, if this just manages to touch this dotted boundary, then collision could be avoided. So, now what is our idea, that let us see when this molecule moves, just imagine it carries a cross section that is equal to, this is R and this is R. For the time being I will write this as RA and this is RB, but actually all molecules are same. That means this distance will be RA plus RB, this is B molecule, this will be again here also. So, this is RB. So, now I have defined one more line here and one more line here. That means, if any molecule, if the center of any molecule like B3 and suppose I call B4 lies just outside this, then there is no collision. That means, no molecule whose center should lie within this cross section, not only this, within this cross section. So, what I will do, that means I will assume that when a molecule moves, it carries a cross sectional scattering cross section with it, a disk with it. So, this disk has a radius of RA plus RB, RA plus RB. So, if any molecule lies within this disk, when this disk moves, it sweeps out a cylindrical volume. If any molecule, the center of any molecule should not lie within this cylinder so as to avoid the collision. So, now let us see, consider a molecule A of radius RA moving along presently that axis is called x axis with V average. So, this is the average velocity by which it is moving. It will collide with all the molecules of B series B series means the colliding molecules is called B series molecules. Suppose I name it as B series molecules. So, it will collide with all the molecules of B series if they lie within the radius of R A plus R B from the line of motion of A. Thus we can imagine a scattering cross section of area pi R A plus R B whole square moving along the molecule A. So, when A moves, it along with A there is a scattering cross section area moving, a disk moving of area this, so that if any molecule lies within this area, within this volume of the cylinder, then it is going to collide, otherwise it will not collide. So, now since all the molecules are identical, so R A is equal to R B, and so the cross section area that is scattering cross section area becomes this R same, that is 2R, so 4 pi R square. So, the radius, the diameter is your 4R and the radius is 2R. So, now our conclusion is scattering cross section is equal to, that area is pi times 4 R square is equal to pi d square, where d is 2R, where d is the diameter of the single molecule. So, you see pi d square is a convenient term and the diameter is also the convenient term in which we can talk. So, now I am interested in, before colliding to another molecule, how much volume is swapped by this area. This is the cross sectional area, scattering cross section area. So, the molecules, suppose it moves certain distance, I will call this distance as L, that is mean free path, and so the moment it comes here, then before that a molecule was here and this molecule has collided, and you see again one molecule is lying within its range. So, without getting collision it moves certain distance. This is what we define this mean free path as. This is the molecule A and this radius is equal to d. This is moving with V average. So, now let us see what is this volume. So, scattering cross section we have now defined at 4d square, where d is the molecule of the diameter of the single molecule. So, now let us calculate the mean free time, that is the time in which it is going to cover the mean free path. So, let us now calculate the mean free time, i.e. the average time after which the molecule may collide with others. So, suppose let us assume a dilute gaseous system which contains n number of molecules per unit volume. So, before colliding with another molecule, the molecule moves certain distance. So, now let us see so that how many molecules will lie within a volume which is swapped by this scattering cross section in unit time. So, the volume which the scattering cross section covers in T time is given by this volume will be given by pi d square, that is the cross section area, into average velocity into time t. So, the volume which the scattering cross section covers in T time is given by T. Suppose in T time this is the mean time, that is the mean time interval between two collisions. So, it will be called mean time. So, covers in mean time is given by V is equal to this time. Now, if you can see this is the volume. So, the total number of molecules in this volume is given by how much? Suppose this is the volume. So, n times this volume is given by 1, because only one collision takes place. So, this is given by 1, implies pi d square average velocity into mean time into n is equal to 1. So, thus we got a formula for mean time. So, thus here I will write, thus T mean, that is the mean time interval between two collisions, is given by 1 by V average by pi d square into n. So, here I have assumed that the molecules are hereby stationary. So, the molecules are hereby stationary. This is the static model. So, now we have seen here, developed this expression for the mean time, that is 1 by V average pi d square n. So, here I have assumed that these molecules, B molecules, are stationary, which is an absurd result. So, we should not actually use this term. So, we have to modify these terms. So, when we consider the motion of all the molecules, then we have to replace this term. So, during the motion of all molecules, V bar has to be replaced by relative velocity, that is V, I will write this as V V relative. So, simply I will write V bar, big V bar, different from this. Actually, it is V bar as average of relative velocity. So, let us calculate. We can't write actually this term. This we can write only when they are stationary. So, when they are stationary, I showed that it will be V bar. But now let us see what correction is needed, because these molecules are also in random motion. So, you see V relative, suppose A molecule is there, this is A and this B molecule is coming with here. So, in the frame of A, if we are sitting on A, if the observer is on A, he will find that B is coming, another B1 is coming like that, another B2 is coming, B3 is coming, another molecule. These are different molecules coming from random directions. So, the relative velocity will be something, suppose I take a single molecule. So, this single molecule of A is moving with V average vector plus V dash, that is of some B molecule, plus 2 V dash cos theta. So, we will use this cos theta term. Now, if I take average of this velocity, you see this term will vanish. So, we will get, these are the velocities of the coming molecules which are also having the average velocities. Then we will write this as V relative square is equal to V average square plus, let us call not V average, first call V A and let us call V B, A and B. So, we will write this as, so you see this, sorry, we will write this as vectorially. This A is moving with some V A and B is moving with. So, let us write this as vectorially. Then if the modulus, if I will take the magnitude, then it will be V again average square plus again V average into V average into cos theta, the average value of cos theta. Now, average value of cos theta is 0. So, this term becomes 0 and so we have V relative whole square, the average of this is again, this is 2 times V average whole square. So, we have V relative, average of V relative is denoted as this, will be root 2 times V average. That means, in place of V bar, if we take the motion of other molecules also, in static model this is okay, but if all molecules are moving, which is obvious, then that will be replaced by this. So, the true expression, true expression of this becomes 1 by, let us call this average as relative. You see this symbol I am using different from this, into scattering cross section pi d square into n is the number of molecules. This is the true expression of the mean time. So, now let us come back to our original diagram where we have considered a single molecule, it suddenly changed its course, then it went back, then again here, then it goes here, then comes here. So, you see these are the places where it collides and then it moves here and there. This is, so now let us see what is the average distance it moves before it collides with another molecule. So, the mean free path that is L is defined as, so average velocity of a molecule into average time before it collides, that is the average time of between two collisions. So, we can write this as average velocity V average into average time interval between, that is T average. So, L is equal to V average by this T is equal to, this is 1 by that is relative velocity, average relative velocity pi d square n. So, this is average relative velocity. So, we can write this as V average. This already we know that is root 2 times V average pi d square n. So, this cancel out. So, the mean free path becomes 1 by pi d square n. So, this is the expression of the mean free path. So, you see here the mean free path is inversely proportional to the square of the diameter of the molecules. More bulky the molecule will be, then the distance it moves before collision will be less. More frequently it will collide, and so that distance will be less.